Well, thank you everyone for coming along and spending your evening with me. And as Mike mentioned, I'm a local in Auckland, and this is actually the 8th version of the talk that I've given around the country. So I really appreciate you spending the evening with me. And I want to give a special shout out actually to my family in the front row here, who have actually enabled me to go on this national tour of New Zealand. So we're nearly there. We finish next week in Napier for the last talk of the series, and that'll take me to 10 in total. So what I thought I would do is what I've actually done at all the other talks around the country, and actually talk to you guys first about the Kaikōura Earthquake in 2016. And ask you, did anyone in this room feel the earthquake? I've got a couple of hands. Okay. And what was the effect for you?
Well, it was tsunami.
Oh, you were in tsunami.
Yeah. And I was having that.
Yeah, yeah. And how about that? What were your experiences? Yeah. I wonder, whenever there's a felt geometry, there's always someone in Auckland. I wonder if that might be you. It's part of the amazing work. So obviously I've been to Christchurch, Wellington, where people felt the earthquake quite intensely. So it woke them up, knocked them out of bed, sloshed them, swimming pools around. But your experience was probably somewhat like mine. So I woke up in the morning, turning on the radio and the TV to hear news about the earthquake. And I was pretty gripped by it. The footage, I'll never forget, of the seafloor lifting up with starfish and lobsters many meters from where they lived was fascinating. And for me, I was really interested by that earthquake and wanted to find out as much as I could at the time. And there's been much work done on that through to a huge team of scientists. And so we know quite a lot about how the earthquake worked, the effect that it had on shore. But what I want to talk to you about tonight is actually what happened offshore. And this might be something you know a bit less about. So I am a Brit, not native to Aotearoa, so I've been here about 16 years. And this is a photo actually that I took of Kaikōura. I'm particularly proud of it. I just want to point out to you the features at the bottom of this image, a whale. It really is there. There we see it. There we see the whale. And so for me, as a non-native person to Aotearoa, for me, Kaikōura is the quintessential image of New Zealand. By that, for me, what I see here is these beautiful snow-capped, really high alpine mountains sweeping down dramatically to the ocean, where we've got this beautiful, pristine coastline, rivers basically coming down those steep slopes to the ocean, bringing huge amounts of sediment. And when we look at the ocean itself, it's a place full of amazing array of sea life and sea mammals and creatures there. And one of the reasons that we've got so much life here is actually to do with its location on the South Island. So we have the Southern Alps coming through the South Island, shedding huge amounts of sediment off the east coast through an array of spectacular rivers that deliver sediment to this coastline. And when that sediment reaches the coastline of the South Island, it gets transported northwards. And it gets transported northward to Kaikōura Canyon. And this is a submarine canyon that has its head in just 30 meters of water. And one of the reasons we've got this incredible ocean life in and around Kaikōura is no coincidence. So this is a place where we bring together sediment push it off into the deep part of the ocean. And as we bring that sediment through to funnel through Kaikōura Canyon, we're bringing food and nutrients with it that feed these systems. And so Kaikōura is a really special place that brings together amazing sea life by virtue of the fact of we've got this sediment delivery to this location. So on just after midnight on the 14th of November 2016, New Zealand's second largest historic earthquake struck just south of Kaikōura. And this was a magnitude 7-point earthquake, so really intense shaking. And the earthquake is one of the most studied earthquakes on the planet. So we know that it ruptured in more than 20 different faults, starting south of Kaikōura and then propagating northeastwards with time, rupturing faults both on the land and offshore on the seascape. The rupturing propagated over about 2 minutes northwards, heading towards Wellington. And as it did so, it intensely shook people's homes, causing localized damage. It also caused devastation to the infrastructure of the area. So here we've got this picture of twisted and mangled railways. Many of you can probably recall the footage of State Highway 1 coming around the coastline, literally being shunted into the sea by a giant landslide. We had enormous amounts of localized uplift of the seafloor. We generated 30,000 landslides, all triggered by this event. For the people that lived in Kaikōura and further to the south, it was fairly devastating. So State Highway 1 was shut for 13 months. So lifelines along that part of the coastline, sort of food and stuff, were really difficult logistically for some time. And locally in Kaikōura itself, a tsunami was generated of about 7 meters high. It was fairly localized, went inland about 250 meters. And for me, the abiding memory I have is of some cows stranded, marooned on an island of land on a farm where there'd been landslides. And they became probably the most famous cows that year in the world. And I can see some of you remember those cows as well. So I'm now going to show you a video, and this is by Brendan Bradley from Quakecore, of a simulation from the earthquake. And I just want you to notice a couple of things. So I'd like you to keep an eye on the timer and the state of the buildings in Wellington. When we look at this, all the red marks the ground shaking acceleration. So this is telling us red means it got really, really shaky. But what I want you to look at with this map is actually the ripple effect on the seafloor. I want you to notice the shaking does not stop when we reach the coastline. And here you can see we're propagating towards Wellington, getting very unpleasant if you're at the top of one of those skyscrapers. But what you can also see is the seafloor has shook a huge amount with this earthquake. So how do we understand what happened to the seafloor with this earthquake then? Well, the key is actually studying the seafloor itself. And this beautiful map of the seafloor, or seascape, as I like to call it, off New Zealand is an absolute beauty. So this is something that I literally spend hours and hours looking at. And for me, it's much like looking at the stars. Kind of the more you look, the more you see. And that's certainly the case for me. And we're really, really lucky to have a map of the seafloor of New Zealand, particularly off the east coast here like this. And this is a map that shows the elevation. We call this the bathymetry and the relief of the seafloor. And this has been made by, thanks to the National Institute of Water and Atmosphere, NIWA, basically crawling along back and forth with their equipment for the better part of a decade and a half, surveying the seafloor. So this looks like a single map. It's actually a patchwork of many small maps put together. But this shows us beautifully what the seafloor looks like. And far from being a barren kind of ramp-like mud-covered wasteland, it's a really, really dynamic environment. So first of all, I want to point out the shallowest part of the seafloor, which is coloured in this lightest colour here. So here we have North Island, and the shallowest part of the seafloor, we call this the shelf. And this goes from your coast to about 150 metres water depth. So this is a place where we feel tides, currents, wave action. Much of the fishing happens here. And the gradient of the slope of the shelf is really low, so less than 1 degree. And if we think about longer term evolution of the continent of our country here, if we lower sea level due to glaciation, all of this shelf pretty much becomes land. So I want you to think about oscillations over time, with glaciations and deglaciations, making this shelf become land and then flooding. The next part of the system that we can see is really dramatic. So this is where we see kind of these stepped cliffs in here. We see dramatic cuts through here. These are our canyons. And we can even see portions of this feature that have fallen down. And we call this the submarine slope. So here we go to about 150 metres water depth, and we drop to more than 1,000 metres water depth in a really, really short distance. So generally less than 5 to 10 kilometres. And we've got this extremely crumpled picture of this slope because we've got a subduction margin. So this is the Pacific plate, this is the Australian plate, and the plate here on the right-hand side is diving beneath the other. Then finally, we've got the deepest part of the ocean here. So we call this the abyssal plain. And this is where I work. So I work in the deepest part of the ocean. So it starts at about 1,000 metres water depth, and it gets deeper as we go all the way up here to about 5.5 kilometres water depth. And again, far from being this barren, muddy wasteland, this is a really dynamic setting. So you can see something on this seafloor here that looks like a river. But this is really, really deep. So as I mentioned, 1,000 to 5.5 kilometres water depth. And then hopefully you can see all these lumps and bumps, and these all represent past earthquakes that are being gradually subducted. Now, when people ask me where I work, I say to them, I can never go to where I work. So what is it actually like down here? So first of all, it's pitch black. It's freezing cold, so it's about 4 degrees on average, crushing pressure, and of course I can't breathe. But if I could, and if I was on the bottom part here looking upwards, what I would be looking up at the slope before me would be one of the most dramatic landscapes that New Zealand has, rising more than 1,000 metres and extending for more than 1,000 kilometres. So this slope would rise up above me, and occasionally things would cascade down that slope and come towards me. So we're super lucky to have this. So I'm just going to play this movie here. And this is a recent reconstruction of what the seafloor of planet Earth looks like itself. And this is part of a UN initiative called Seabed 2030, which has been tasked with trying to map the world's oceans. So this started in 2017. And in 2017, only 6% of the planet's ocean floor had been mapped itself. As of right now, we're at about 25% been mapped. And the reason I want to show you this is because you see how rugged, how much terrain and relief there is on the sea floor itself. And this is only about 25% being mapped. But what I want to do now is actually take us to the other side of planet Earth to look at the North Atlantic. So this part of the sea floor between Northwest Europe and the Eastern American seaboard. And I want you to notice that between the two, you've got what looks like a mountain range. And this is the mid-Atlantic ridge where we've got lifting of two plates moving apart. And in a really weird coincidence with Hochstetter, I want to take us there, and I want to take us back to 1858. So when Hochstetter was doing his mapping on Donkey in and around Auckland, there was something absolutely incredible happening in the North Atlantic. So I want you to envisage that you are all Victorian people living in this part of the world. And you may be living in the UK, or you may be living in Ireland and have family in the east coast of Canada. And if you need to get an urgent message to them, it will take a minimum of 10 days to send that message via ship. And that's assuming fair weather. So and often the weather is not fair in this part of the world. So sending urgent messages between the two continents could take several months. And obviously this was a pretty tricky thing for people to deliver. So the British and the US governments spent 20 to 30 years funding the installation of the transatlantic cable. And this shows you the relief over which that cable had to pass over the Atlantic to join the two together. Now, in 1858, the public and press of the day were obsessed with this. So the more modern sort of analog to this would be the Apollo 11 moon landing in 1969, where for the very first time, humans were going to touch down on the moon. I know some people weren't alive then, some people were, and they can probably fondly recall watching the TV. The excitement about the installation of this was absolutely insane. So Tiffany, the jewelry makers, who some of you in the room will definitely know, they make really nice ladies' jewelry. They made thousands and thousands of souvenirs to mark the installation of the cable. And you can see it's actually got chunks of the cable itself, and they sold in their thousands. So people were really obsessed with this. So 1858, it comes time to turn on the cable. So they turn on the cable. The first message is transmitted from Ireland over to Canada, and it's a message from Queen Vic herself saying something obscure, and it took about 2.5 minutes to deliver, and people were just so excited. Now, the cable lasted for 3 weeks. Not long, but if you're interested in it, it's a fascinating story. But one bright spark of an engineer, uncertain if it was at the British end or the US end, decided to turn the voltage up to speed things along. And unfortunately, overheated the wire, broke the system, and the whole thing broke. Now, in a strange echo of the times we live in today, there were actually cable deniers. Once the cable failed, who believed it didn't exist, which is a commentary on the human condition, I think. So, but by the 1860s, the engineers had sorted out the design of the cable. And there were many cables coming between Northwest Europe and Canada, and many coming into Newfoundland itself. By the 1920s, there were dozens of these cables connecting the two continents together. So on the 18th of November, 1929, there was another earthquake. So this is a story of earthquakes. This time a magnitude 7.2. And this struck just south of Newfoundland, where the cables were coming in, about 250 kilometers south. And the earthquake itself wasn't too devastating. So there were a few chimneys that collapsed. But what was devastating was about 2.5 hours after the earthquake, a tsunami approached the southern part of Newfoundland. And the bays and inlets of this peninsula called Burin Peninsula were very long and elongated. So what that meant was the 7-meter tsunami, when it reached those bays, it became streams. And as it became squeezed, it became higher. So it became a 13-meter tsunami, which caused the devastation. So it struck 40 villages. So here we can see houses literally picked up and transported inland over fields. About 28 people died, and it sort of destroyed their local fisheries. So pretty devastating for the people that lived there. But at the same time, the cables also felt the effect of this. So the transatlantic telecommunication companies reported that 12 cables snapped. 6 of them snapped instantly when the earthquake struck. And then another 6 snapped in succession going from north to south in the following 13 hours. And so people didn't really understand how the earthquake, the tsunamis, and the cables kind of all worked together. And it took about 20 years for these 2 guys, Bruce Heason and Maurice Ewing, to come up with an interpretation of what happened. And obviously there were some rather large world events that turned down between 1929 and 1952. And this is a copy of their paper. And just to say, Heason and Ewing are kind of oceanography godfathers. So here is a map of Newfoundland itself. And here is that Burin Peninsula. So this was the place that felt the devastation from the tsunami. So just to get your eyes in onto this map, we can see a series of lines here that mark contours. And we're going from 1,000 meters water depth down slope towards 6,000 meters. So a really steep, deep and steep part of the ocean. And where we see the star here, this was the center, the epicenter of the earthquake. And what Heason and Ewing hypothesized had happened was when the earthquake struck, the initial 6 cables broke and were broken by a large submarine landslide. And they were able to map that, and it had an area of about 20 square kilometers. But that landslide didn't stop moving down the slope. And they surmised that that landslide somehow started to accelerate down the slope, ingest water, and turn into something that I want you to think of as an avalanche in the ocean from the sea floor, but one made of sediment. I want you to think this is a sediment avalanche. And so they came up with this idea that it was this sediment avalanche that snapped all the rest of the cables with time. And they calculated that the landslide and the sediment avalanche together moved 200 cubic kilometers of sediment. And it was that caused the tsunami together. Now that sounds like a big number, and it is a big number. So to put it into context, that's 30 times more sediment than all of Earth's rivers deliver to the ocean every year in one event on the seafloor. So significant. But this isn't the only example. So in 1979, Nice, so southern part of France, moving out to the Mediterranean, at the airport, part of the runway collapsed into the Mediterranean. Can anyone recall this news at the time? I had one Frenchman in Wellington who knew this very well. So this time, this wasn't caused by an earthquake. This was caused by an intense rainfall event. And part of the runway had been built on reclaimed land. And that intense rainfall caused a submarine landslide at the upper part of the slope. Now, because this happened in 1979, oceanographic techniques had moved on quite a long way. So they were able to see on the seafloor what happened. And like Grand Banks, cables also snapped here. So there was a cable that snapped 3 hours and 8 hours after the landslide. And what this showed when they looked at the seafloor, that indeed the very upper part of the slope had a submarine landslide. So obviously in Auckland, we are really very familiar with landslides as of this year. But I want you to imagine ones on the ocean. they really don't need much of a slope to move. So on the ocean, we consider a steep gradient something above 4 degrees. So think it's submerged, it's got water, things can slip and slide very easily. So what they could see offshore Nice was these landslides initiated, it didn't stop moving. And it started to move and break up and turn into something we call a debris flow. And it didn't stop moving. It kept moving even onto the slope where that slope had no gradient whatsoever. And what they found were the deposits of the thing that Eason and Ewing had called a sediment avalanche, which is called, the name that we call it now is a turbidity current. This is not a very intuitive name. So why is it called a turbidity current? One is it's turbid, so it's milky, you can't see through it, it's opaque. And the other reason is it's turbulent. So I want you to imagine a seething turbulent mass on the seafloor where we've gone from a landslide, which is kind of like moving soil that starts to move faster and faster, ingest water, and at one point we ignite the flow and it becomes turbulent. Now, these things are kind of hard to imagine. So I'm going to show you an experimental one that we've made in a flume tank. So I want you to think of this as a big, very long, narrow fish tank. And here is this sediment avalanche, this turbidity current coming towards us. So it's this seething, broiling mass of sediment and water, really turbulent, really energetic. So I want you to imagine you're a seafloor right here in front of this. You're a starfish. We're going to get hit by the shockwave right now. If that doesn't take you out, the flow might. So it might rip you up off the seafloor and start to transport you in. If you're a very tenacious starfish holding on, you will become buried by the sediment within this flow. So this is a turbidity current. And to give you a bit of context, that was 0.5 meter wide and 1 meter high. So back to the Kaikōura Earthquake. So can the ideas from Grand Banks and Nice help us understand what happened on the seafloor of Kaikōura? So this is a map from this brilliant New Zealand Geographic article on the earthquake itself, mainly focusing about what happened onshore. But the reason I've shown this is I want to point out, so here in green, we have the very edge of the South Island. And all of these circles mark all the different ruptures of the fault, with the more red showing the more intense shaking. But what I'd like you guys to note is actually the shelf has an awful lot of circles. So what this is showing us, the shaking intensity on the sea shelf was very, very intense, particularly in and around this feature here, the Kaikōura Canyon. So let's start. So if we think about Grand Banks, earthquake, shaking, what do we see? So this is a map of the Kaikōura Canyon. So just to help get your eye in, this is Kaikōura itself, so the little peninsula, and then this is the head of the Kaikōura Canyon, so 30 meters of water depth. And this is some work published by Josh Mountjoy at NIWA shortly after the earthquake. Now, this is a bathymetry map of the seafloor, so showing the relief. And the colors that we can see on here is something that we call a difference map. So the seafloor of the Kaikōura Canyon was surveyed before the earthquake, and then it was surveyed shortly after the earthquake. And what a difference map shows us are differences in height between those two maps. So everywhere where we have red colors, there has been erosion and removal of sediment. Everywhere where we have the blue colors, there's been localized deposition and build-up of sediment. And in the upper part of the canyon itself, there was up to 40 meters of sediment removed during the earthquake. which is an incredible amount. Think about the height of this room. I'm not sure how much we would estimate this to be. So if we just zoom in right to the very upper rim of the Kaikōura Canyon, we have a before and after image of what it looks like. Now, you don't need to be a marine geology expert to understand these images. You can be an artist. So I just want to help you interpret these. So I want you to think of this as the rim of the canyon. You can see kind of blurry and smooth. And what this is showing us is that that rim was kind of covered in a layer of mud. So think of it as a snowflake. It was soft. There weren't sharp pieces. But if we look at this map after the earthquake, we can see a very rough-looking surface. And what this is showing us is a whole series of sparks of landslides in the upper part of that canyon that have collapsed down. And Josh and the team that worked on that paper interpreted that the amount of sediment that collapsed through the canyon itself was about 850 metric megatons, so a decent amount. And also, just to say, it isn't all about evacuation and removal of sediment. So the eagle-eyed amongst you will have definitely noticed there are sites of deposition in here. And Josh and his team are kind of working on these. But this speaks to perhaps a continuation out of the canyon. And indeed, in some follow-up work that we've been involved with, we actually have found evidence for canyon collapse in every single one of these canyons that have been overlaid with a green polygon. So in total, there were a landslide collapse in 10 simultaneous canyons. So some of you may be wondering, how do you know this? Well, in one of the strangest coincidences of my career, the team were actually at sea on an expedition looking for evidence of past earthquakes on the Hikurangi subduction margin. And this is part of a bigger project where we're trying to understand if it's possible for there to be a magnitude 9 earthquake in the Hikurangi subduction margin. So just to put that in context, because I can give you these numbers and they're probably meaningless. So this is the Hikurangi subduction margin deformation front. And a magnitude 9 rupture would involve about 1,000 kilometers of rupture at the same time. So the whole interface would fail at the same time. And this is where the expedition had been. So all of these yellow dots that we can see on the slope itself were sites where the team had cored. So we'd cored 50 cores. Oh, and just to go back, these were Monique, Aratrika, and Simon, who were postgrad students at Auckland working with me, who were on the voyage. I wasn't on the voyage. So of course, I wake up, I hear about the earthquake, and my first thought is of the students on the ship. I had visions of the Tangaroa, Niwa's vessel, literally surfing a tsunami. I was very concerned. So there were a few nervous hours where we didn't have contact, but it was all good. They were in deep water at the time, so 4,000 or 5,000 meters water depth, didn't feel it. And the decision was made by the chiefs of the voyage, Phil Barnes and Alan Orpin, to abandon the expedition. So you can imagine this is a big call. These expeditions cost a lot of money, big teams of scientists. But they made the call to abandon expedition and head back towards Kaikōura Canyon. So these last few cores that you see here, to see if there were the deposits of these sediment avalanche, this turbidity current on the seafloor. So this was the first time since 1929 that there was the opportunity for someone to actually go and test this idea. So this is the first place that they cored. And here we've got a video of on board the Tangaroa of that core. So this was quite a long core. So this is about 4.5 meters. Here's Aratrica. This is Jenny Hopkins, a colleague from Vic, working on the tephra. So here, this is in the sedimentological lab. We're cracking open the core and taking a look at the fresh deposits that we see here. So when they first chucked the gear over the side of the ship, they didn't know if they would pull anything up. So here we can see layers of soft, fresh sediment. But this isn't the deposit from the earthquake. This is. So just to help you get your eye in, this is a photograph of the sediment core. This is a CT scan, and then this is a graphic log that combines the observations of the two. And just to say, so we CT scan all of our cores. Normally we don't break them, we bring them back. And it is a bit awkward going to Auckland and Wellington hospitals with these cores of mud. So our most favourite place is we go and CT scan them at veterinary CT scanners, and we use one in Dunedin where they literally scan cows. So, just, a few things that aren't moving and breathing with a bit of mud on is all good. So how did we know that this was the super fresh deposit? So this was a 4-day-old deposit from the sediment. And the first thing to say is when they pulled it up, everything above this orangey yellow line was like soup. So it was very difficult material to actually pour. So it was still depositing itself. And if you look at the photo just beneath that line, hopefully you can see there's a slight sort of rusty orangey colour here. And this actually marks the oxic layer that formed the former layer of the seafloor. If you look at the CT scanner, so just to say the reason this has been a game changer for us is because we can fly through our cores without destroying them. So we can do a lot of analyses without destroying them. So again, you don't need to be a sedimentology expert to understand it. Hopefully you can see in the bottom part, if I ask you to describe it, there's lots of blobby bits, and a clear white line here. And what these sort of murky blob things, sorry, Kathy, are all of the footprints of tiny organisms that live in the sediment, on the seafloor, and they destroyed and messed up the sediment. But for the eagle-eyed amongst you, you may have spotted a shadowy light film emanating from the former seafloor and ejecting up through the event bed itself. And so this is a little organism that made its way out and escaped and lived, which is fantastic. We also did some short-lived isotopes. So we did thorium-234, which has a half-life of 23 days, and lead-210, that showed us that these are really, really young deposits. And we even had dying kinner, shallow marine organisms in there. So in the months and years after the earthquake itself, we've been back a few times. So I'm just going to show you a few images. So everywhere above this yellow line is the deposit from the earthquake itself. So these were very fresh, 4 to 5 day old deposits. We went back 7 months later. This is my favorite one. You can see beautiful layers. We went back 3 years after. You can see these CT scans are just exquisite of these. So in total, since 2016, we've been back on 9 voyages, either partly or wholly tasked with sampling these deposits from the earthquake. So this is really an unprecedented opportunity for us. So this has involved more than 80 scientists combined on these expeditions, involving many postgrad research students from Auckland, from Victoria, and from Canterbury. Huge numbers of technicians aboard the Tangaroa, NIWA's vetting themselves, world experts. The voyage leads have done really the heavy lifting for this work, a huge amount of organisation for each one. That includes Phil Barnes, Alan Orpin, Katie Meyer, Laura Wallace, Jamie Howarth and Scott Nodder. And you can imagine once we get all these cores back to land, that's only the beginning of the work. So then we have to scan all the cores, so we scan them for their geotechnical properties, we scan them for CT, we scan them geochemically, and we do most of those down at a scanning facility called Orca in Dunedin. And we also, Bruce has worked with us here, and whose work I'm going to come to now. So, so did these landslides stop in the canyon, or did they carry on going? And some of you, I did hear some lovely oohs when I pointed out the thing that looked in the deep ocean like a river. And this feature is something we call the Hikurangi Channel. And you were right to ooh and ah. It's one of the most beautiful submarine channels in the world, and it's one of the longest. So New Zealand has huge submarine channels. So these are carved into the seafloor by huge, powerful turbidity currents that have the ability to erode enormous amounts of sediment and carve these channels into the seafloor. And so the question that we were wondering was, did these landslides evolve, accelerate, and ignite into turbidity currents that then moved through the Hikurangi Channel itself? And in order to answer that question, we've been working with Bruce on looking at foraminifera. So these are amoeboid organisms with a shell that can either live in the water column or on and in the seafloor. And the ones that live on and in the seafloor are called benthic foraminifera. And Bruce has been working with us on these deposits to look at the kinds of foraminifera preserved within the deposits themselves. And through much detailed work, he has been able to discern at least two different sources for these foraminifera. So a population, so if you've got any questions about this, Bruce can answer them for me, just to say at the end. But so he was able to discern populations that live in this location, which we'll call for now the Cook Strait Canyon area, and a population that lived in this area, which we'll call the Kaikōura Canyon area. And if we go along the channel and look at our more distal core sites, so again, I'm going to give you an idea of scale. So distance from the Kaikōura Canyon, here we're at about 350 kilometers. Here we're at 700 kilometers. So this is like a supersized Waikato River. It's 4 times the size, basically. And if we go downstream, this helps us unravel where the origin of these flows has come from. And actually what Bruce found with his work was incredibly, when we go to this most distal site where we have this really thick, so this is more than 70 centimeter complicated deposit, that actually the first foraminifera and sediment that arrived to the site were from the Cook Strait Canyon area. These were then overlain by foraminifera and sediment that were sourced from Kaikōura. And this was a little bit of a surprise to us initially, because the earthquake itself initiated just south of Kaikōura, propagating northeastward, ending about here. So what that meant was the landslides triggered in the southernmost canyons first, and then successively with time we had collapse to the north. But what we didn't factor in was how fast these flows moved. So these flows move somewhere between, we think, about 20 and 70 kilometers an hour. So actually, the landslide collapse in the Cook Strait area had a 200-kilometer head start on all the material that had collapsed here. And so it's been really interesting to kind of unravel where the sediment has come from with time. And if people want to ask me about how the flows evolved, we're still working on it. So we know it's complicated. Things came through from different sources, caught up, mixed, and deposited. and deposited some very, very complex deposits. So if anyone is a geologist in the room, and you may recall, and I know some of you are, because I lectured you quite recently and tortured you with the boomer sequence, this is unlike, as far away from that deposit as you could possibly get. So it's a really exciting opportunity for us to work on this. So with the work, so much work is carrying on with this, but we can answer some big questions about this. So how far did these flows travel through this system? So as of 2017, our most distal core site was 700 kilometers from source, but this was the site of our thickest deposit that we found. So this was 75 centimeters. So we knew that the flows had to have continued a lot further. And last year, Katie Meyer of NIWA led a voyage going all the way to the end of the Kaikōura Canyon. Again, to provide context, it takes a week for the ship to transit between these sites. So it's an enormous distance. And indeed, she found the event bed right at the end. It was really thin, 2 centimeters, and it was really boring layer of mud with nothing else in it. But what that tells us, incredibly, these flows sourced from these collapsed canyons were able to make it all the way through the entirety of this channel. How big were the flows? So this is quite a difficult question for us to answer. So we're not a super sedimentology research team, unfortunately. We don't have tens of millions of dollars to monitor the ocean floor. We're in New Zealand. But what we can do is make some estimates based on the morphology, the shape and depth of the channel itself. So in places, so this is what the Hikurangi channel looks like in cross-section. And I'm just going to nip back to this image. We're just to this really interesting place where the channel makes this really strange handbrake turn to the right. And here, the channel is about 100 meters high. At its deepest, it's about 200 meters. But if we go back to Bruce's work, here, we actually got deposits at least 60 kilometers away from the edge of the channel itself. So that makes us think that these flows were probably several hundred meters thick. So I don't want you to think of these as being like rivers. I want you to think of these valleys that are channeling avalanches. And these avalanches are in water, so they're not flat, they're flat. But it's likely that the flow lofted up an even finer clay mud plume into the water column above it. And I lead another project working just here, where we're actually looking at evidence for past earthquakes over the last 2 million years. And we're looking at a very long core that's 900 meters long here, and another one just on top of this knoll. This is called Turanganui Knoll, and this is an old volcano that sits about 1,000 meters above the seafloor. And what we get preserved on there are these deposits of the muddy plume that's been thrown up into the water column. So probably the mass of the body is several hundred meters thick, but has a muddy plume about 1,000 meters in the water column. So how long might these flows have lasted for? Well, again, we don't know because we can't measure them. But based on other canyons in the world where the super sedimentology research groups with loads of money can monitor these flows, is we know that they go between 20 and about 70 Ks an hour. So if we take that range and assume the flows started in Kaikōura, moved all the way through, the flows lasted for 17 to 66 hours. But recall the clay plume that I mentioned lofted up into the water column. So if we assume that that was 1,000 meters, we don't know, and then we assume it's made of clay, that will take 13 years to deposit. So while the flow itself was relatively short, we're actually still depositing the flow. And I've made a huge assumption here and assumed there are no currents in the ocean here. which I know is wrong. So that deposit is still falling out of the water column. So what about the ecosystem? So you recall my spectacular nature photography image at the beginning, showing us that how special this place is. Well, lucky for us, NIWA had been working here for many years. Their ecologists had been working in this location. So we're back to the very head of the Kaikōura Canyon. And everywhere here where we've got a blue polygon on the map marks a space in the Kaikōura Canyon where the biomass is 100 times higher than any other seafloor environment 500 meters or lower, except black smokers. And so this is an incredibly special place. And when I say biomass, I'm talking sea cucumbers, weird wormy things. That's my A-level biology teacher not being very impressed with me there. That's as far as I can take you. And the reason we've got such rich biomass is that sediment bringing all this food and nutrients to feed it. And you may recall, this is exactly ground zero of where we had 40 meters of removal of sediment. So Katie Bigham was a recent PhD student at Vic who just finished. And she worked in the upper part of the Kaikōura Canyon here on a whole series of transects that they'd been working on before and after the earthquake to see the effect of the devastation. As some of you may have heard about this, it was in the media about 3 months ago now. And what we're looking at is a photo of the seafloor at the same place, 10 years before the earthquake, 10 weeks after, 10 months after, and 4 years after. And each of these different colored circles mark the location and type of organism that's living at that spot. So here, before the earthquake, we can see lots of benthic organisms living in the seabed and on the seafloor, feeding fish, pinna type things, starfish. But if we look 10 weeks after, all of that has gone. So the devastation was immense for those benthic communities. All we've got is a couple of rather hungry fish. But 10 months after, you could see shoots of life starting to re-emerge on the seafloor. And 10 years after, 4 years after, sorry, you can see a real intense richness of life. Now, Katie, for her PhD work, has modeled how long the recovery will take in the upper part of the canyon. And she modeled that somewhere between 4 and 12.5 years after the earthquake, the canyon will have undergone full recovery for its benthic organisms. Now, the eagle-eyed may have spotted that the colors of the organisms are different. And she struck a very beautiful balance in her article stating that the diversity may have changed forever with the removal of that sediment, but there is a big richness of life. So this is really interesting. It suggests the organisms are really in tune with the collapse from the landslides in the canyons. So if we go further down the channel where we've worked, have we got evidence for life after the earthquake? And so some of these cores are from 7 months to 3 years afterwards. And as a sedimentologist as I am, what I like to see is these beautiful straight lines of structures, not these weird, blurry, blobby lines and shadows, because what these mark the imprints and footsteps of organisms that are living, eating, and destroying the sediment. And so it's actually really good. In fact, you can probably see the silhouette of the organism captured here in the core as well. But this result has been really surprising for us in the deep, because so I come originally from working at these outcrop, and kind of the sort of common view is that when these flows come down, they're so devastating that they remove life, and it takes a long time for it to come back. But what Katie Bigham and what we're finding in the deep also is almost the opposite, that the ecosystems in these environments are really attuned to these events. And it's a bit like a bushfire. They almost need these things to come through, deliver food, nutrient to the system to set things off again. So it's been a fascinating find for us. So to conclude then, so I've been working on these deposits of these sediment avalanches that are somewhere between 5 days old and 500 million years old. And what I've learned so far with working on the deposit from the Kaikōura earthquake is that these deposits allow us to understand the connection to the land and the deep ocean and how these flows actually link to the life in those ecosystems that obviously affect us. So thank you. Mike, are you coming back? Or do you want me to? Why don't I? Hey, Bernard.
Kaikōura is a very famous place for upwelling.
Yes.
What? Just remembering the pictures of the organisms. What was it perhaps not like that? Does the recovery from the hinge of the upwelling to Kaikōura is probably a very famous place? And another place to think what they did.
I think that's a very good question, Bernard. And I actually think Kaikōura is a very special place, actually. So we've been really surprised, first of all. So I think where it is physically and the nature of the canyon and how it's funneling stuff down and obviously allowing upwelling up through the canyons, I think is the perfect mix to allow that sort of high biomass there. Cook Strait, much less so, yeah. Yeah, yeah. There's Bruce waiting for a forum question. Oh, hey.
Hey, so the 9 earthquake, when the whole place falls down, what is inside there?
So just to say, yeah, the work for the paleoseismology kind of got put to the side when this happened, but the first PhD student who's working on it has just finished. So we had some master students work on it. And we've managed to put together a record for about the last 3,000 years of earthquake. And we don't have evidence. And she's called Charlotte Pizer. She was at Vic, and she's worked at onshore and offshore to try and connect the two. And we don't have evidence for a magnitude 9 in that time frame. We do have evidence for a magnitude 8.6, however. So there's good news and there's not so good news. Yeah, so she's written that paper up. That's the last paper of her PhD, and she's going to be submitting it soon. But she's just started another job. So yeah.
So what's happened between 8.4 and 9?
So quite a lot, actually. I couldn't tell you how much rupture length is on an 8.6 off the top of my head, but it is a logarithmic scale. So there's actually quite a big difference. Bernard might be able to. Have you got any ideas? Not sure. Oh, James might know. No. Okay. Yep. Okay. Well, I don't think we've got any questions, so I might draw the, oh, one more. Oh no. So let's just go to a regional map. Oh, which is obscured. So what you've got to think about is time, first of all. So remember I was mentioning when there's a glaciation, the coastline of New Zealand goes all the way out to the edge of here, and we become one island, first of all. And what that means is where we have large river systems, many of them go all of the way out to that coastline. So I'm just going to go to the north part of the margin here. So where we've got Mahia Peninsula, when we go right out to the edge, can you see there's actually a canyon here? This is called Mahia Canyon. It's likely when sea level was low during our glaciations that the rivers make it all the way out to the edge. And actually at the head of each one of these canyons is the river. So they're literally pouring huge amounts of sediments right there. And then I want you to imagine we've got bigger storms, we've got slightly different currents going on. But in this project that I'm working on up here, where we're looking over multiple glacial cycles, what we've shown, so the thickest deposit we found from this earthquake was 75 centimeters. Where we work up here, when it was the last glacial maximum, the deposits were 7 meters thick. And the events happened every 40 years. So what this is showing us is when we look at, I think, when we look at these canyon systems, we're actually looking at kind of these conduits that are carved out into the margin during times when our sea level has been lowered, when our glacier is bigger. And we're almost looking at these kind of relic seafloor canyon systems today that couldn't be carved by those flows. They don't have quite as much erosive power. So they were an order of magnitude bigger, and they occurred much more frequently. But the interesting thing here is, I think some of these canyons on the margin have been here a long time, but as subduction continues, so this plate moves beneath the two, this slope is actually uplifting and evolving. And so it's actually driving the transport and erosion and incision down it. So it's a bit like you're building mountains on the seafloor and your rivers want to carve all the way down to here, to the deepest part of the ocean. So there's a lot of potential to erode. But interestingly, the Hikurangi Channel has shifted over time because it used to be on this bit of seafloor that has been subducted. So that's basically tucking in the trough of the subduction margin. So this will have a cell body. Yeah, it is building up. Yeah. So it's building its levees in places. Yeah, in places. And the reason it has this weird kink is two reasons. This is over-thickened oceanic crust coming through, which is actually one of the reasons that we've got such uplift here. And the other is this feature, this is called the Luatoria debris avalanche, which is huge. It's like a huge chunk of the shelf and slope fell down, but actually it didn't stop there. It's made it all the way through here. And here, again, where we're working, is a 100-meter thick deposit. And basically that blocked up the whole system as well. So we do think older versions try to go straight north, but we're getting this thicker crust coming through and we've got a big blockage. Cool. Yeah. These? so these aren't real. This is me playing with ArcMap to try and make this look quite dramatic. But some people would go, oh, they're contorites. So thank you, everyone. And it is late. I know people have to go. So thank you very much. And yeah.